Hello, fellow teachers. We are the team Free Notes, which means no gravity, no limits, and no fear. My name is Jiang Mengxi.
My name is Lai Kai Zhou.
My name is Li Yingqi.
And the name of our experiment is the rotation and deformation of Slinky. There are totally three parts of our experiment. The first one is free falling, the second one is the contraction, and the last one is the rotation. So for the first part of our experiment is about the free fall of a spring. In the gravity environment, when we hold the top of the spring, we notice that spring stress due to the influence of gravity. If we release it at this moment, we observe that the spring first contracts to its bottom before falling downward. This occurs is because the speed of the spring tensions attacks and acts is faster than the speed of the gravitational effect, which is why we see the spring fully contract before entering free fall. This leads us to wonder, in the outer space with zero gravity, can we still observe this phenomenon? Our result is that without the influence of gravity, spring cannot undergo free fall, and therefore this phenomena cannot be observed in space. Additionally, without any extra force acting on it, the spring is influenced only by its own tension and remains in a fully contract state.
And this is our second experiment. Holding the slinky as shown in the video, if you let go of it in space, it will float due to the low gravity environment, and also only receive the force from itself retracting. To start this experiment, start by holding both sides of the slinky with both of your hands and stretching out your arms. Then do the procedure below, which includes three releasing methods. First method is to release your right hand first, then followed by the left. Second is to release your left hand, then right. Lastly, try to release both of your hands at the same time. The main idea of this involves that in theory, any site of imbalance in force when releasing or any timing difference will cause the slinky to drift toward the side with the stronger force, and that on the ISS, where there is no gravity, this outcome will be more drastic and be easier to observe. And plus, if you manage to balance both sides, you may be able to see it neither move or rotate, in contrast to seeing it just falling so quickly on Earth.
In our third experiment, we first held the spring vertically and then devised two different methods. The first method involved rotating the rest so that only the top half of the spring stretched outward due to the swing, while the lower part point toward the center of the circle. The second method involved rotating the entire arm, allowing the spring to follow the floor rotation of the arm. In both methods, we observe how the spring moves without the influence of gravity. We aim to use these two experiments to explore how spring performs circular motion in the absence of gravity. We hypothesize that the spring might get taller and taller as it rotated. This concludes our report on the proposal. Thank you for your attention.